Implement advanced STP modifications and mechanisms. Topology, and I would use GNS3 with image iOS BL2. I will drag three switches. Okay, D1, D2, and A1. D1, the host name. D1, D2, and A1. Right, and connect between D1 and D2 gigabit 101. In my case, I will use gigabit 01. Between D1 and A1, gigabit 5, 6, and fast Ethernet 1 and 2. I will use 1, 1 to 1 and 1, 2 to number 2. And from D2 to A1, 5 and 6, 3 and 4. Okay, I will use 1, 1 to 3 and 1, 2 to 1, 0. Okay, and show the interfaces. Okay, and the connection to PC on port 23 on A1. Okay, PC. Port 23, but I will use the last. Okay, I will use port 23. Required resources, 2 switches, 3650. I'm using image, this image, iOS BL2. 1 switch 2960. Also, I'm using image iOS BL2. 1 PC, I'm using a virtual machine on VirtualBox. Okay, cables, Ethernet cables. Build a network and configure basic device settings. For switch D1, configure this. Okay, so copy all this to a notepad. A notepad. Okay, this is for switch 1. Okay, the host name, banner, spanning tree, rapid, very long spanning tree. Line console, no exit timeout, login synchronous. The range of interfaces, in my case, the range of interfaces is different. Okay, this is the range of interfaces from 00 to 03, from 10 to 13, from 20 to 23, and from 30 to 33. Okay, so in this case, shut down all interfaces in the switch. I will shut down all interfaces in my image gigabit from 0, 1 to 03, from gigabit from 00 to 03, from 10 to 13, from gigabit 20 to 23, and gigabit 30 to 33. And set 3 interfaces to trunk. These interfaces gigabit 0, 1, 1, and 1, 2. Gigabit 0, 1, 1, 1, and 1, 2. Switch port mode trunk, no shutdown, exit. Create a second VLAN and set an IP address. Enter, switch 2. Okay, the banner and line console interface. Shut down all ports, so use the same and use this configuration the same as the previous switch. Okay, this for the trunks, the same trunks 0, 1, 1, 1, and 1, 2. So copy this 0, 1, 1, 1, and 1, 2 for trunks. Okay, second VLAN and IP address. And on switch A1, banner, rapid console. Shut down all interfaces. Okay, use this. Shut down all interfaces. And the ports connected to another switches trunks. Okay, gigabit 0, 1, 0, 2, 0, 3, and 1, 0. 0, 1, 0, 2, 0, 3, and 1, 0. From gigabit 0, 1, 0, 2, 0, 3, and gigabit 1, 0. Okay, 4 ports. 1, 2, 3, and 1, 0. 1, 2, 3, and 1, 0. Mode trunk, the second VLAN, and IP address. Now start the switches. Start this. Start this another switch, and this another switch. Okay, double click on D1. Okay, enable configure terminal. Once you are on global configuration mode, copy the basic configuration. Copy, then right click to paste. Switch port mode trunk, command rejected. An interface whose trunk encapsulation is auto cannot be configured to trunk mode. Okay. Remember on these switches, on layer 3 switches, when you configure mode trunk, configure previously switch port trunk encapsulation at 1Q. Okay, and add this to all trunk configurations and other switches. Okay, and enter again this configuration, the trunk configuration, right click, okay, enter. It's very good. And D2, enable configure terminal. Copy, right click to paste. Okay, very good. And A1, copy, enable configure terminal, right click to paste. Okay, very good. All commands accepted. Okay, save the running configuration to store up configuration. Okay, do this on real app. Outputs and spanning tree topologies highlighted in this lab may be different. Discover the default spanning tree. Your switches have been configured, interfaces have been enabled, and Redbit spanning tree has already converged onto a loop-free logical network. Before proceeding with the lab, you need to be informed of what the spanning tree topology looks like. You need to know where the root bridge is and where the root designated and alternate ports are on each segment for each VLAN. It may be helpful to draw this information out. Okay, and you can do the following. Go to D1 and show spanning tree space. Okay, okay, on VLAN 1 bridge ID, this is the base address, the base MAC address of D1, the switch D1. Okay, and this is the base MAC address of the root bridge. Okay, and the base MAC addresses are different. So D1 is not the root. Okay, and look at the ports. Gigabit 01 alternating, alternate, gigabit 11 root, and gigabit 12 alternate. Okay, 11 root. 11 is the root port. 12 alternate, and 11 alternate. Go to D2. Okay, and on D1, for VLAN 2, the configuration is the same. Okay, go to D2 and show spanning tree space. Okay, base MAC addresses are different, so this switch is not the root switch, it's not the root bridge. And look at the interfaces. 01 is designated, 01 designated, designated, D2, gigabit 11 root and 12 alternate. 11 is root, 12 alternate. On D3, sorry, A1 and show spanning tree, enter space. Okay, base MAC addresses are the same. So this bridge is the root. This bridge is the root. Okay, the root bridge. And ports, all designated ports. Okay, all ports on the root bridge are designated ports. Okay, very nice. Implement and observe various topology tuning methods, controlling the root bridge. The current root bridge was selected based on the lowest bridge ID, consistent of the priority extended system ID equal to the VLAN ID and base MAC address values. Okay, for example, on A1, the priority, the extended system ID, in this case is 1, and the base MAC address. This is the base MAC address. With the priority and extended system IDs being identical, the root bridge MAC is numerically smaller than the logical bridges MAC. Okay, compare. Look at this MAC address 004DD34EF00. Should be a lower value than the other switches. Okay, 000DDF8. And the root A1 is 004DD34. Okay, this is 004DD3 and this is 004DDF. So the value of D1 is higher than A1. Okay, that is higher than A1. And review the D2 004DDB3 and on A1 is 0004DD34. So the hexadecimal number, the MAC address on D2 is higher than A1. So that's why A1 is the root bridge. The result is that in a completely unconfigured network, one single switch will be elected as the root bridge. The resulting choice of switch may or may not be desirable. There are two basic ways to manipulate the configuration. The spanning tree VLAN VLAN ID priority value command can be used to manually set a priority value, and the spanning tree VLAN ID root, primary or secondary command can be used to automatically set a priority value. The difference the two is that the priority command will set a specific number multiple of 4096 as the priority. This number must be an increment of 4096. The root primary command will set the local bridge's priority to 24,576. If the local bridge MAC is lower than the current root bridge's MAC, or 4096 lower than the current root's priority, if the local bridge MAC is higher than the current root bridge's MAC. And notice that 24,576 is the sixth increment of 4096. The logic behind this operation is straightforward. The root primary command tries to lower the priority only as much as is needed to win the root election, while leaving priorities between 24,576 and the default 32,768 for use by secondary bridges. The command always takes the entire bridge ID into account when computing the resulting priority value. The spanning tree VLAN ID root secondary command will statically set the local bridge priority to 28,672 in an otherwise unconfigured network where all switch priorities default to 32,768. The root primary command will set the priority on the switch to 24,576 to 4,096 increments lower than the default priority, while the root secondary command will set the priority on the secondary route to the 28,672, 4,096 increment lower than the default priority. Modify D1 and D2 so that D1 is selected the primary root bridge for VLAN 1 and D2 is selected the primary root bridge for VLAN 2. D1 should be elected as the secondary root bridge for VLAN 2, and D2 should be elected as the secondary root bridge for VLAN 1. So you will need to make configuration changes on both D1 and D2. The commands used D1 are as follows. Okay, on D1 for VLAN 1, set the root primary, and for VLAN 2, the root secondary. Okay, go to D1, configure terminal, spanning -3 for VLAN 1, the root primary, and for VLAN 2, root secondary. And go to D2, configure terminal, spanning -3 for VLAN 1, root secondary, and for VLAN 2, root primary. Okay, root primary. After you have configured both D1 and D2, go to A1 and issue the command show spanning tree root. In this output, you will see the root bridges differentiated. Okay, go to A1, show spanning tree root. Okay, the root port for VLAN 1 is gigabit 01, and the root port for VLAN 2 is gigabit 03. From the output, you can see that the root port for VLAN 1 is gigabit 01, and the root port for VLAN 2 is gigabit 03. Okay, the root for VLAN 1 is gigabit 01, this port, and the root for VLAN 2 is gigabit 03. Okay, for VLAN 1 gigabit 01, and for VLAN 2 gigabit 03. Okay, very nice. Okay, and remember D1 is the root bridge for VLAN 1. And D2 is the root bridge for VLAN 2. Okay, so that's why A1, the root port, is facing root bridge 1, and the root port on A1 is facing the root bridge on VLAN 2. Adjust port cost values to impact root and designated port selection. The network is implemented right now. There are two direct paths between switch A1 and the root bridge for each VLAN. Path and port costs are evaluated to determine the shortest path to the root bridge. In the case where there are multiple equal cost paths, the root bridge, additional attributes must be evaluated. In our case, the lower interface number. For example, gigabit 01 is chosen as the root port, and the higher interface number. For example, gigabit 02 is put into a spanning tree discarding state. Okay, the question is why gigabit 01 is the root port on VLAN 1 and not gigabit 02. Both ports have the same cost, the same port cost, but the difference is that gigabit 01 is a lower number, is a port with lower number, so it's preferred. Okay, so that's why gigabit 01 is the root port. You can see which ports are blocked with the show spanning tree VLAN ID command or the show spanning tree blocked ports command. For now, examine VLAN 1 on D1. On A1, issue the commands show spanning tree VLAN 1 and show spanning tree blocked ports. Okay, go to A1. Show spanning tree VLAN 1. Okay, only information about VLAN 1. The root is gigabit 01, root gigabit 01, gigabit 02, 03, and 10 alternate ports. Okay, all other ports for VLAN 1 are alternate ports. And show spanning tree blocked ports. Show spanning tree blocked ports. For VLAN 1 gigabit 02, 03, and 10. Okay, 02, 03, 10. Very good. And for VLAN 2 gigabit 01, 02, and 10. And for VLAN 2, if the root port is 03, the alternate ports are 02, 01, 02, and 10. Okay, for VLAN 2. As you can see, VLAN 1 has its root port on gigabit 01. The another 3 ports are alternate blocking ports. To manipulate which port becomes the root port or non-root bridges, change the port cost or port priority value. Remember that this change could have an impact on downstream switches as well. Do not make these changes in a production network without careful planning and prior coordination. On A1 shutdown interfaces, gigabit 01 and 02 assign a new port cost of gigabit 02 and then issue no shutdown to the ports. Okay, shutdown gigabit 01 and 02. Okay, these two ports, gigabit 01 and 02, shut down. And gigabit 02 change the cost to 12. Okay, and A1 on real lab is a switch, 2960 switch with fast Ethernet interfaces. And for fast Ethernet interface, fast Ethernet 02, the cost is 19. Okay, and if you want to configure this with a lower value, you will set the cost to 12. In my case, on A1, this image has gigabit interfaces. So if I want to configure gigabit 02 with a lower cost, in this case, the cost by default is 4 for gigabit interfaces. And if I want to configure a lower value for gigabit 02 on A1, I need to set a lower value like 2 or 3. Okay, so shutdown interfaces, set the cost on gigabit 02 and enable both interfaces. Okay, configure terminal interface range gigabit 01 and 02. And enter shutdown interface gigabit 01. Interface gigabit 02 and spanning -3 cost and set the cost a lower value than 4. In my case, I will use a 2. Enter exit and set the range again of interface range gigabit 01 and 2. No shutdown. Enter exit. Okay. Now verify. Show spanning tree VLAN 1 and show spanning tree VLAN 1. Now you can see gigabit 02 is the root, the cost is 2 and is preferred than gigabit 01 because the cost on gigabit 01 is 4. Okay, now the root is gigabit 02 with a lower cost. Blocked ports. Blocked ports. Only gigabit 01 is blocked. Okay, why? For VLAN 1 only gigabit 01 is blocked. Okay, because gigabit 01 is on alternate role. Gigabit 02 is root and 03 designated, 10 designated. Okay, verify again. Show spanning tree VLAN 1. Show spanning tree blocked ports. Okay. From the output, you can see that the root port selected by A1 for VLAN 1 is now interface gigabit 02, and the port and root cost is now 2. There is another impact to the cost being said. It has been issued the command show spanning tree root on A1. Okay, show spanning tree root. Okay, and now you can see for VLAN 001, the root port is gigabit 02 and root cost 2. For VLAN 1, gigabit 002 is the root port, and for VLAN 2, root cost 4 and gigabit 03. Okay, 03 for VLAN 2, the root. Okay, because the root bridge is D2 and gigabit 03 is the root for VLAN 2. Because D1 is the root bridge for VLAN 1, gigabit 02 is the root port for VLAN 1 on A1. And because D2 is the root bridge for VLAN 2, so gigabit 03 is the root port on A1 for VLAN 2. Notice that the root port for VLAN 2 is now fast Ethernet 2. Okay, and the lab is fast Ethernet 2. In my case is gigabit 03. Okay, don't worry about this. In my case is gigabit 03, the root port for VLAN 2, and because the total path cost to D2 via fast Ethernet 2 is now 16, which is less than the cost of the direct link to D2 via fast Ethernet 3 or fast Ethernet 4. Okay, I will explain this. Very easy to explain this. And I will use a pocket tracer to. I will use a pocket tracer to show only the graphics. Okay, you have this this topology, D1, D2, and A1. D1, D1, D2, and A1. Okay, D1 and D2 3650, A1 2960. And use the connections, gigabit 101, 101. Okay, and 56, 56, 1, 2, 3, 4. Five, 6, 3, 4, 6 to 4. Okay, and D1 is the root bridge for VLAN 1. Root bridge for VLAN 1. And D2 is the root bridge for VLAN 2. Okay. The cost for gigabit interfaces by default is 4. Okay, The cost for gigabit interfaces, so the cost in this link is 4. The cost is 4. And by default, the cost for fast Ethernet interfaces is 19. Cost is 19. Okay, and for VLAN 1, if root bridge is D1, the root port should be on this part, on A1, close to the root bridge, fast Ethernet 1 and fast Ethernet 2. So fast Ethernet 1 is preferred. Okay, so fast Ethernet 01, fast Ethernet 01 is the root port for VLAN 1, the root for VLAN 1. Okay, but to prefer fast Ethernet 2, the cost was changed to 12. Okay, so now the lower cost is preferred, and now fast Ethernet 2 will be the root port for VLAN 1. Fast Ethernet 2 will be the root port for VLAN 1. Okay, and now the question is, what is the root port for VLAN 2? If the root bridge for VLAN 2 is a D2, the root port is placed on the port with the lowest path. Okay, look at this. Fast Ethernet 3, the port cost is 19, and also the path cost is 19 to reach the root bridge for VLAN 2. Okay, so the path cost here is also 19. Okay, how fast Ethernet 3 reaches the root bridge for VLAN 2? The path is 19. But if you see with from fast Ethernet 2, the path cost is 12 plus 4 and is 16. So the path cost to reach the path cost is 16 because it's equal to cost 12 plus cost 4. Okay, the path cost is 16. Okay, from fast Ethernet 2 to reach the root bridge for VLAN 2 is cost 12 plus cost 4. Okay, using this path. So the path cost is 16 and is a lower value of path cost 19. Okay, the path cost 19. So fast Ethernet 2 is also preferred for the root port for VLAN 2. And now fast Ethernet 2 also preferred for fast Ethernet 2 is also preferred for the root port on VLAN 2. Okay, so that's why says, notice that the root port for VLAN 2 is now fast Ethernet 2. Okay, fast Ethernet 2 instead of fast Ethernet 3. Why? Because the total path cost to D2 via fast Ethernet 2 is now 16. Okay, 12 plus 4 is 16, which is less than the cost of the direct link to D2 via fast Ethernet 3 or fast Ethernet 4. Okay, so 16 is a lower value than 19. Okay, but in my case, the route for VLAN 2 is gigabit 03 because this is a gigabit interface. The cost here is 4. Okay, 4. And the cost here is I change it to 2. Okay, 2. And the cost here is 4. Okay, the path cost on VLAN 2, the path cost to reach the root bridge on VLAN 2 for gigabit 03 is the path cost is 4. This direct link, but for gigabit 02 is 2 plus 4, that is 6. So cost for the path, the path cost 4 is preferred over 6. So that's why gigabit 03 is the root port for VLAN 2. Okay, in my case, gigabit 03 is the root port for VLAN 2. And adjust the cost value of interface fast Ethernet 2 on A1 to 18. This will make the VLAN 2 root port fast Ethernet 3 again. Okay, so we change fast Ethernet 2 on A1 to 18. The cost was 12 and changed to 18. If you change the cost for fast Ethernet 2 to 18, for VLAN 1 is preferred over 19, but for VLAN 2 to reach the root bridge on VLAN 2, the path cost is 18 plus 4, that is 22. 18 plus 4, 22. And 22 is a higher value than the direct link path cost 19. So now fast Ethernet 3 will be the root port. Fast Ethernet 3 will be the root port for VLAN 2. Okay, because 19 is lower than 22. Okay, and in my case, gigabit 03 is the root port for VLAN 2. Okay, on A1. Adjust port priority values to impact root port selection. The next method to impact root port selection is configured on the root bridge itself. In our current network topology, A1 has 2 connections to the root bridge for VLAN 2. Switch D2. The root port has been selected, in this case based on the lowest port ID. Port ID is made up of two values, labeled as priority, and NBR is the number. Okay, this value, priority and number. The lowest priority and number are preferred. The port number is not necessarily equal to the interface ID. A switch may use any port number for STP purposes if they are unique for each port on the switch. The port priority can be any value between 0 and 240 in increments of 16. Older switches may allow settings the priority in different increments. On A1, issue the command show spanning tree VLAN 2. Okay, go to A1, show spanning tree VLAN 2, enter. Now you have this information. And look at this, fast Ethernet 3 is the root port. For VLAN 2, in my case, gigabit 03 is the root port for VLAN 2. As expected, with two equal cost paths to the root bridge, the lower port ID was selected as the root port. Okay, and look at my topology. Gigabit 03 and gigabit 10 has the same cost. Okay, 4. Okay, gigabit 03 4 cost 4 and gigabit 10 cost 4, but gigabit 03 is the root because the number is 4 is a lower number than 5. Both have 128 is the priority, but 4 is preferred over 5. Okay. Modify the port priority of D2 interface gigabit 106 so that it becomes the preferred port. Okay, change the root priority on D2 interface 6. In my case is I'm using, instead of using 6, I'm using gigabit 12. Okay, on D2, change the priority on gigabit 12. Okay, shut down both interfaces 5 and 6. In my case, shut down gigabit 11 and 12. Go to D2 interface range gigabit 11, 11 and 12. Shut down. Exit. Now on 6, change the priority to 64. On interface gigabit, in my case is not 6. In my case is 12. Spanning tree port priority 64. I am not changing the cost. I am changing the priority. Okay, let's see what happens. Enter and exit. And now no shutdown on both interfaces. In my case 11 and 12. No shutdown. Okay, exit. issue show spanning tree belong to on A1. Go to A1, show spanning tree belong to. Now you will see that fast Ethernet 4, in my case, gigabit 10 is now the selected root port. Okay, gigabit 10 is the selected root port. Okay, gigabit 10 now is the root port for VLAN 2. Okay. This selection is based on the lower priority value of D2 interface, gigabit 106. Okay, you changed the priority on gigabit 12, and now gigabit 10, this link is preferred, and gigabit 10 is the root port for VLAN 2. Notice that the lower priority value does not appear in any A1 output. Okay, because it's configured on D2. Okay, and anyway, verify this on D2 and show spanning tree VLAN 2. And now you can see gigabit 12. The priority was changed to 64. The priority is lower. Okay, is lower than 128, and 64 is preferred. Implement a spanning tree port fast. In both STP and RSTP, a newly connected port must be guaranteed not to create a switching loop before it can become a forwarding port. This may take up to 30 seconds. However, such a check is not necessary for ports connected to end devices that do not perform switching or bridging, such as workstations, network printers, servers, etc. In RSTP, these ports are called edge ports. Ports that connect to other switches in the topology are called non-edge ports. Edge ports can safely enter the forwarding state right after they come up, because they do not connect any device capable of forwarding frames. Cisco developed a feature called portfast that essentially allows you to define a port as an edge port. Any portfast enabled port will enter the forwarding state immediately after coming up, without going through the intermediary non-forwarding states, saving 30 seconds each time a new connection is made to the portfast. Portfast can be used with all STP versions. Apart from allowing a port to jump into the forwarding state as soon as it is connected, the concept of an edge port is extremely important in RSTP and MSTP. Recall that as part of its improvements over legacy STP-RSTP uses a proposal agreement mechanism to rapidly yet safely enable a link between switches if one of the switches has its root port on that link. Upon receiving a proposal on its root port, a switch puts all its non-edge designated ports into the discarding state, effectively cutting itself off from the network and preventing a possible switching loop. This is called the sync operation. When this is accomplished, the switch sends an agreement back out its root port so that the upstream designated port receiving this agreement can be immediately put into the forwarding state. The switch will then start sending its own proposals on all its non-edge designated ports that have just become discarding. It will wait for agreements to arrive from downstream switches, which will allow these ports to instantaneously become forwarding again. If end devices are connected to ports not configured as edge, that is port fast, these ports will become discarded during the sync operation. Because end hosts do not support RSTP and cannot send back an agreement, they will be cut off from the network for 30 seconds until the ports reach the forwarding state using ordinary timers. As a result, users will experience significant connectivity outages. Ports configured as edge ports are not affected by the sync operation and will remain the forwarding state even during the proposal agreement handling. Activating RSTP in the network without properly configuring ports toward end host as edge ports will cause the network to perform possibly even more poorly than with legacy STP. With RSTP, proper configuration of ports toward end hosts and edge ports is critical. Cisco switches default to all their ports being non-edge ports. Ensure that PC3 is turned on. Okay, so start this PC. This is a virtual machine on VirtualBox. Open VirtualBox before this. The body Linux PC. On settings, be sure on network is not attached, or also you can use generic driver, UDP tunnel, and be sure this cable is connected. Okay, check this. Okay. Okay, very good. And on A1, issue the command debug spanning tree events, then issue a shutdown command for interface 2.3, wait a few seconds, and issue the shutdown command, followed by end and undebug all. The log output will appear something like the output below. Okay, first on A1, remember the port I'm using is gigabit 2.3. Okay, on A1, debug spanning tree events. Enter. Go to configure terminal interface gigabit 2-3. Now shutdown. Enter. Okay, shutdown. Enter. Okay, and undebug all. Okay, undebug all. Okay, now when you enable the port connected to the PC, RSTP initializing port is now a designated port. and transmitting a proposal. The port is up, transmitting the proposal. Line protocol up, transmitting proposal. Okay. Expired, transmitting proposal, expired. Okay, shut down the port. A port is administratively down. Line protocol down. What you see here is the switch trying to go through the proposal agreement process on 2.3, but there is no point in this because the device connected to the interface is an endpoint and does not understand spanning tree. This adds the potential of 30 seconds delay before the host can send data such as DHCP requests to the network. Okay, you can see no shutdown is 15 minutes 17 seconds, and look at 15 minutes 47 seconds, 30-second delay. On A1, issue the command debug spanning tree events, then configure interface fast Ethernet 23 with spanning tree port fast, and no shutdown. This designated 2.3 as interface that will never be connected to another switch, and therefore it will never cause a loop in the topology and subsequently allow that interface to go into forwarding mode immediately. Okay. Debug spanning tree events, enter, configure terminal. In my case, is interface gigabit 2.3, spanning tree port fast. Okay, don't worry about this message and no shutdown. Enter. Initializing port 2.3. 2.3 is now designated. Interface up, line protocol up. From the output, you can see that our STP sees 2.3 as designated. It never sends proposal on the interface because of the port fast setting. There are two other ways to configure interface as a port fast port, using the switch port host interface configuration command and using the spanning tree port fast default global configuration command. Switch port host not only enables port fast, but also statically set the interface mode to access and disables aggregation protocols. The spanning tree port fast default command sets the default state to interfaces that are configured as access ports with port fast enabled. All you must do is configure the interface with switch port mode access and port fast is engaged to that interface. Verify that a port is port fast mode can be done by looking at the running configuration for that port or by examining spanning tree details for the port. Example, use the show spanning tree interface command to verify that the interface is on edge mode on A1 and show spanning tree interface, in my case gigabit 2/3. Okay, this is edge mode. Okay, designated forwarding. Or use show spanning tree detail and show the section for the interface. show spanning tree detail, and pipe and section gigabit 2 3 enter. Okay, gigabit ethernet. And now port gigabit 23 on VLAN 1 is designated for forwarding. Okay, and you can see show spanning tree detail, space here on 12 gigabit 23 designated for forwarding, and the port is in port fast edge mode. Implement and observe various topology protection mechanisms. Implement and observe root guard. Root guard helps prevent the root switch or root port takeover. It is configured on the port that is to be protected. If a port that is protected by root guard receives a superior Vpdu that would normally cause the port to become a root port, the Vpdu will be discarded and the port will be moved to the root inconsistent state. An STP inconsistent state differs from the error disabled state and that the port is not disabled entirely. Instead, it is only put into the blocking discarding state and will be put back into its proper role and state. Once the cause for its inconsistent state disappears, with root guard, a port will be reinstated into its appropriate role and state automatically when it stops receiving superior Vpdus. Vpdu root guard is a protective mechanism used in situations where your network and the network of your customer need to form a single STP domain, yet you want to have the STP root bridge in your portion of the network, and you do not want the customer to take over this root switch selection, or back up the connectivity in your network through the customer. In these cases, you would put the root guard on ports toward the customer. However, inside your own network, using root guard would be harmful. Your network can be considered trustworthy and there is no root switch to protect against. Using root guard in your own network would cause it to be unable to convert on a new workable spanning tree if any of the primary links failed. And it would also prevent your network from converging to a secondary root switch if the primary root switch failed entirely. To illustrate the behavior of root guard, we will configure it on designated port D2 for VLAN 2. D2 is the root bridge for VLAN 2, so all trunk ports are designated. On D2, show spanning tree root. Okay, go to D2, show spanning tree root. For VLAN 2, no root ports, because all ports on the root bridge are designated ports. Show spanning tree detail, include VLAN 0002. Okay, and show spanning tree detail pipe, include VLAN 0002. Now, ports on VLAN 002, 3 ports, designated ports, gigabit 01, 11, and 12. Gigabit 01, 11, and 12. Go to A1 and verify that. Go to A1 and verify what is the root port for VLAN 2. Okay, we'll go to A1, a spanning tree root, include only VLAN 0002. Okay, is gigabit 10. Okay, as expected, gigabit 10 is the root port for VLAN 2. Now, on D2, add root guard to the ports connected to A1. Okay, interface range, the range of these 3 ports, and spanning tree guard root. Okay, these 3 ports, gigabit 01, 11, and 12. On D2, configure terminal interface range, gigabit 01, gigabit 11 and 12, and spanning tree root guard, enter. Sorry, guard root. Okay, exit. Okay, and guard root enable on these 3 ports. To verify that root guard is working, try to have A1 take over as root bridge for VLAN 0002. Issue the command spanning tree VLAN 2 priority 16,384. Okay, go to A1. Configure terminal spanning tree VLAN 2 priority 16,384. Okay, enter. Okay, and transmitting proposal. Okay, return to D2 and issue the command show spanning tree VLAN 2. Okay, transmitting proposal, go to D2 and show spanning tree VLAN 2, enter. Okay, show spanning tree VLAN 2. All ports are designated ports. But look at the state is BKN, it's broken, and the type is root inc, is root inconsistent. Again, show spanning tree VLAN 2. This output has 2 indicators of the issue. First is BKN is the short for broken, and root inc represent the root inconsistent message. A list of STP inconsistent ports, including the reasons for their inconsistency, can also be requested with the command show spanning tree inconsistent ports. Okay, show spanning tree inconsistent ports. Okay, all ports are inconsistent for VLAN 1 and VLAN 2. These 3 ports are the inconsistent ports for VLAN 2, and they are the same ports on this side. To return things to normal, issue the command no spanning tree VLAN 2 priority 16,384 on A1, and then remove the root guard on interfaces. On interfaces on D2 with the command no spanning tree guard root. Okay, and go to A1, go to no spanning tree VLAN 2 priority 16,384. Okay, and go to D2, configure terminal, And the range of interfaces gigabit 0, 1, 11, and 12. Gigabit 0, 1, 11, and 12, 3 ports. No spanning tree word root. Okay, exit. Implement and observe Vpdu word. Port fast causes an interface to go into forwarding state immediately. There is a risk that if two port fast enable ports are inadvertently or maliciously connected, they will both come up as forwarding ports immediately, creating a switching loop. The default expected behavior of a port fast port that receives a Vpdu is for that port to revert to a normal spanning tree non-edge port. There is the potential that the load on a given switch may be too great to handle the received Vpdu properly, prolonging the loop condition. Vpdu ward adds another layer of protection whenever a port protected by Vpdu ward unexpectedly receives a Vpdu. It is immediately put in error disabled state. Any interface can be protected with Vpdu ward, but is typically used in port fast enabled ports. Vpdu ward can be configured globally or on a per interface basis. If the Vpdu ward is configured on the global level using the spanning tree port fast Vpdu ward default command, the Vpdu ward will be automatically enabled on all port fast enabled ports of the switch. If the Vpdu ward is configured on an interface using the spanning tree Vpdu ward enable command, it will apply to this port unconditionally, regardless of whether it is a port fast enabled port. For this example, we will configure Vpdu ward on a trunking interface that is a non-root port on A1. Configuring Vpdu ward on an interface that is intended to be a trunk is not a recommended practice. We are doing this just to demonstrate the functionality of the tool. Verify the trunking ports and root ports on A1 using the commands show spanning tree root and show interface trunk. Okay, go to A1 and show spanning tree root. Enter. Okay, for VLAN 1 root port is gigabit 02 and for VLAN 2 gigabit 10. For VLAN 1 gigabit 02 and for VLAN 2 gigabit 10. And show interface trunk space. The trunking ports, 4 trunking ports on A1, 4 trunking ports on A1. From the output, we see that interface gigabit will meet the requirements for this demonstration, non-root and trunk. Okay, gigabit 01 is trunk and is not root port. Okay, no root port and is trunk. Gigabit 01. So apply the configuration on A1 on gigabit 01. Apply the Vpdu word. Configure terminal interface gigabit 01 and spanning tree Vpdu word enable. Enter. Okay, and receive it Vpdu on port gigabit 01. Error disabled Vpdu word error detected on gigabit 01. Line protocol down. Interface changed state to down. Okay, so the interface receives a Vpdu word and goes to error disable state. As you can see, the interface is almost immediately error disabled. Issue shutdown command remove Vpdu word with the no spanning tree Vpdu word enable command. No shutdown command and, and verify the trunk is operational with show interface trunk. Okay, and interface gigabit 01 shutdown. Apply no spanning tree, Vpdu word enable, and no shutdown. Okay, and show interface trunk. And now, okay, interface up, line protocol up, implement and observe Vpdu filter. Neither port fast nor Vpdu word prevents the switch from sending Vpdus on an interface. If such a behavior is required, Vpdu filter can be used. It can be configured either globally or at a specific interface. If Vpdu filter is configured on the global level using the spanning tree port fast Vpdu filter default global configuration command, the Vpdu filter applies only to port fast enabled ports. When these ports come up, they will send up to 11 Vpdus and then stop sending further Vpdus. If the Vpdu filter configured interface receives a Vpdu at any time, the Vpdu filter and port fast will be deactivated on that port, and it will become a normal spanning tree interface. As a result, a globally configured Vpdu filter does not prevent ports from receiving and processing Vpdus. It only attempts to stop sending Vpdus on ports where most probably there is no device attached that would process them. If you configure interface with the spanning tree Vpdu filter enable command, the port will stop sending and processing received Vpdus altogether. This can be used, for example, to split a network in two or more independent STP domains, each having its own root bridge and resulting topology. However, because these domains are no longer protected against mutual loops by STP, it is the task of the network administrator to make sure that these two domains are never connected by more than just a single link. For this demonstration, we will configure Vpdu filter at the interface level. Okay, use this command, show spanning tree interface, the interface connected to the PC, detail, pipe, include Vpdu. Okay, show spanning tree interface. In my case, the interface connected to the PC is gigabit 2.3, gigabit 2/3. Detail pipe include Vpdu. Case sensitive. Enter. Okay, look at this. Vpdu sent 2804 and received 0. Okay, and repeat. Now send 2811. Again, 2814. Configure the interface with Vpdu filter using the spanning tree Vpdu filter enable. Okay, configure terminal interface gigabit 2.3 spanning tree Vpdu filter enable. Exit and repeat the command. Repeat the command, show spanning tree interface 2.3 detail, include Vpdu. Enter. Vpdu sent 2826. Wait a moment and then repeat the command again. And it's not incrementing. Okay, very good. Repeat again the same value. Remove the Vpdu filter with no. Okay, configure terminal interface to 3. No spanning tree. Vpdu filter enable. Exit and verify that Vpdus are now being sent. Okay, 2833, 2835, 2836. Very nice. Implement and observe loop guard. Loop guard prevents root and alternate ports from becoming designated ports if Vpdus suddenly stop being received on them. In a normal STP network, all ports receive and process Vpdus. Even blocking discarding ports. This is how they know that the device at the other end of the link is alive and still superior to them. If a blocked port stops receiving these Vpdus, it can only assume that the device on the other side is no longer present and they are now superior and should be in forwarding state for the given segment. An example of when this could occur is the instance where the Rx, the receiver fiber in an optical cable becomes disconnected, cut or connected to a different port or device than the corresponding TX, the transmitter fiber, creating an unidirectional link. This could cause permanent switching loops in the network, so loop guard helps to prevent them. Loop guard can be enabled globally using a spanning tree loop guard default global configuration command or per interface basis using a spanning tree guard loop command. Loop guard should never be enabled on port-fast enabled ports. For this example, we will configure loop guard on an alternate port on A1 and then stop sending out Vpdus from the corresponding designated port on the other end of the link. Verify which ports are alternate ports for VLAN 2 on A1 using the show spanning tree VLAN 2 command. Okay, on A1, show spanning tree VLAN 2. Okay, alternate ports gigabit 01, 02, and 03. Okay, for VLAN 2. Okay, for VLAN 2, alternate gigabit 03, 02, and 01. 03, 02, and 01. On A1, configure interface gigabit 01 with loop guard. Okay, interface gigabit 01 spanning tree loop guard or guard loop. Configure terminal interface gigabit 01 spanning tree guard loop. Exit and on D1, configure the port connecting to gigabit 01 for Vpdu filter. In this topology, the interface is the interface connected to gigabit 01 the interface on D1 is gigabit 11. Configure with Vpdu filter on D1. Okay, go to D1, interface gigabit 11. Enter spanning tree Vpdu filter enabled. Go to A1 and look at this. Okay, receive with info expired. Loopward blocking port gigabit 01 for VLAN 1. Okay, gigabit 01 is now designated, received, expired, now designated. On A1, you should receive a syslog message stating that loopward has blocked the port gigabit 01. Issue the command show spanning tree VLAN 2, and you will see that gigabit 01 is broken. Okay, on A1, show spanning tree VLAN 2, and gigabit 01 is broken. Loop inconsistent. Show spanning tree inconsistent ports. Show spanning tree inconsistent ports. Okay, look at this. Inconsistent for VLAN 2 gigabit 01. Show spanning tree VLAN 2. Show spanning tree VLAN 2 gigabit 01. On D1, remove Vpdu filter. Okay, go back to D1 and exit. Interface gigabit 11. No spanning tree Vpdu filter enabled. Okay, and go to A1. Now you can see initializing gigabit 01. Receive it superior Vpdu on gigabit 01. Gigabit 01 is now alternate. Okay. Repeat show spanning tree VLAN 2. Okay, before was designated broken, loop inconsistent, and now is alternate blocking state. On A1, you should see syslog message indicating loopward has removed the block on interface gigabit 01. Remove the loopward configuration. Okay, show spanning tree inconsistent. Show spanning tree inconsistent ports. No inconsistent ports. And remove the loopward. Configure terminal. Interface gigabit 01. No spanning tree word loop and okay, thank you very much.